So now that we have identified the different dimensions that an environment can take, we're going to take specific examples of agents to see whether we can identify the dimensions of the environments that these agents are going to operate on. Specifically, we will look at 4 agents: an agent trying to solve a Sudoku game, an agent playing a poker game, and an agent trying to do internet shopping, and then finally an agent trying to drive a taxi automatically. So we have this in a table, and we will be asking the question, trying to identify the particular dimension that we can categorize a particular agent into. So starting with fully observable or partially observable, how will you categorize these 4 different agents? Do you think they are fully observable or partially observable? Okay, so to begin with, let us remind ourselves what is meant by fully observable and partially observable. If an agent sensors give it access to the complete state of the environment at each point in time, then that environment is said to be fully observable. Otherwise, it is partially observable. So clearly, this Sudoku game is an example of a fully observable environment, because at any one time you can see the full 9x9 board, you can see the numbers that are inside, and it will help you to know what move to make or what kind of row or cell you're going to fill in. Okay, so there is nothing that you cannot see in that board at any particular time. So this is going to be fully observable. Compare that with the poker game. Obviously, the poker game, each agent will have only a few cards at a time, and you only know the cards that you have. You don't know what your opponent has. So obviously, this cannot be a fully observable environment. It is only partially observable. Okay, next is the internet shopping. So we assume an agent is trying to shop for a set of items using the internet. Is it a fully observable environment or not? Obviously, it is not fully observable. At any one point, you can only see the items that you are able to the system is able to display for you on the screen. You cannot see other items at that same instant. Okay, you have to move to the next screen, and so on. Maybe when you left the other screen, by the time you go to the next one, another shopper may have bought that item, so that item is no longer available. So anyway, clearly this is not fully observable. You can only see a portion of the items at one point. Similarly with the taxi driving, you cannot see the entire road from your source to destination. You can only see a portion of the environment at a time. Yeah. So in terms of partially observable or fully observable, clearly only Sudoku game is fully observable and the rest are partially observable. The next question is, are these environments or the environments under which these agents are supposed to operate, Are they deterministic or stochastic? So again, to help you, remind you the definition of deterministic or stochastic environment. It says if the next state in the environment is completely determined by the current state and the action executed by the agent, then the state is said to be deterministic. Otherwise, it is stochastic. Okay, so the next state should be determined only by the current state and the action that the agent is going to take. So let's take the agents one by one. The agent that is trying to solve Sudoku game clearly is deterministic, because if you have a board, let's say currently it has about 50 cells filled in, and now the agent decides to fill a particular cell with a given value, then the next state will be the resulting state after entering that value, nothing else. Alright, so this Sudoku game clearly is deterministic. Next state is determined only by the current one and the action of the agent. Can you say the same about the poker game? Is it deterministic? Obviously no, because it depends on the action of other agents. So it is not deterministic. Similarly, internet shopping is not deterministic, because the state you are right now, or the state of the environment, doesn't depend on you only determining to purchase the current item or not purchasing it. It is dependent on the other agent also trying to do the same shopping at the same time. And similarly with the taxi driving, it is not deterministic, because there are many road users on the road. The action you take doesn't necessarily tell you the next state. Let's say, for example, you try to accelerate, while at the same time another agent try to block your way. Okay, so the next state is unknown actually. So for being deterministic or not, again, only Sudoku is deterministic, the rest are stochastic. Poker is stochastic, internet shopping is stochastic, and so also taxi driving. The next dimension is whether the environment is sequential or episodic. So again, let us remind ourselves the definition of this sequential or episodic. An agent action is said to be episodic if it is divided into atomic episodes. Decisions do not depend on previous decisions or actions. Right, so looking at these games, Sudoku game clearly is sequential, because you have a sequence of cells that you must fill in. Okay, yeah, so, and actually the order you solve those cells sometimes is important. You can only know the answer of some of the cells after you solve some of the cells. Okay, for example, if you were able to deduce that a certain cell should have 4, then you know that the remaining cells cannot have 4 again, because each cell has to have a unique integer or digit within that row or within that column or within that small box. Right, so you can say Sudoku game is sequential actually. Poker game is also not episodic. Okay, your action depends on the action of other players. So you cannot divide the action that you have to take as an agent into a set of independent episodes. No, there's no independent episode. The choice you make depends on the choice of other agents that are playing the same poker game with you. However, if you look at the internet shopping, it is clearly episodic. From the start, an agent will have a list of items to purchase. And all we want is that he should, by the end of the shopping period, he should purchase all of these items. Now, him purchasing item A first doesn't affect the next item he's gonna he's gonna purchase, because these are independent items he has to purchase. So purchasing item A, then item B, then item C is the same as purchasing C, then B and A. Each of these is independent, so it can be considered therefore as episodic. Purchasing one item doesn't affect the purchasing of another item. He has to purchase each one of them anyway, and the order is not important. Whereas, for example, in Sudoku game, the order is actually important, because he cannot identify what should be in a cell, in a certain cell, without identifying others that are easier to deduce at the beginning. So what about taxi driving? Clearly, taxi driving is not episodic. It's a continuous process that you cannot even break it into, kind of steps that has to be followed. It's a continuous thing. So it cannot be episodic, it is sequential. So this is the answer for that. Sudoku is sequential, poker is sequential, taxi driving is sequential, only internet shopping is episodic. Right, the next question is whether the environment is static or dynamic. So again, to remind ourselves, the environment is said to be static if it remains unchanged while an agent is deliberating on the next action he's going to take. Okay, so an agent has perceived an input and he is trying to decide what action to take based on this facet. The question is, while he is still thinking of the action to take, or still trying to decide what action to take, will the environment change or not? So that determines whether the environment is static or dynamic. Sometimes we said the environment may not change, but his score may change while he takes more time trying to decide. So that is called semi-dynamic. But we're not concerned about that here. We just want to decide, is it static or dynamic? So for Sudoku game, definitely it is static. The value, as we said earlier, the values that should be in each cell is fixed from the beginning. All that the agent is trying to do is to identify what is it exactly. But the amount of time he takes in deciding the value that should be in a certain cell will not affect, will not change the environment. The environment will remain static. So Sudoku is static. So what about the poker game? Again, the poker game is going to be, the environment is unchanged while the agent is trying to deliberate what to do. Okay, the other players will wait for him to make a move before they make their own move. Okay, each player is taking a turn. So clearly this is static. The environment doesn't change while a particular agent is thinking what to do. Right, what about internet shopping? Is it static or dynamic? Alright, clearly this is dynamic. You may find an item that you think you want to buy, but maybe another agent is also deciding on that item. So if you spend too much time before you decide, the other shopper could take that item and buy it, and you may lose it. Alright, so internet shopping is dynamic. The environment is changing all the time. In fact, some shopping website, they will give you a time limit. Okay, you have put this in the cart, but you have to purchase it within this number of minutes, otherwise it will be sold. Taxi driving, is it static or dynamic? It is continuous environment, so it cannot be static. It is dynamic. Things are changing with the time. Okay, yeah. So while you are thinking what to do after you, for example, see another driver in front of you hitting a brake, you have to decide what to do, and you taking too much time before you decide the action to take could make you actually hit that particular vehicle. Yeah, so it is a dynamic situation. All right, the next item is, or the next dimension is discrete versus continuous. So again, let's remind ourselves of the definition. If an environment consists of a limited number of distinct, clearly defined environment states, okay, relative to time, the percepts, and the actions, then the environment is said to be discrete. Otherwise, it is continuous. All right. Now, clearly, almost all of these agents are discrete. I think only the taxi driving is continuously changing environment. But the Sudoku doesn't change with time, as we said. Similarly, poker game, it doesn't change with time. Internet shopping is a discrete environment, and the taxi driving, on the other hand, is continuous. So this is the answer for this one: discrete, 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 and continuous for the taxi driving. And the final one is whether the environment is single agent or multi-agent. When is it single agent? If an agent is operating by itself alone in the environment. Otherwise, it is multi-agent. And we saw that multi-agent could be cooperative or competitive. Again, clearly only Sudoku is single agent. One agent is trying to solve the Sudoku game. But poker game normally consists of multiplayers. And as we said, internet shopping, even though you don't see the other shoppers, they are there purchasing the items. So if you act too slowly, the item may be purchased by the other shoppers and you will lose it. So it is multi-agent. There are many agents at any one time trying to do the purchase. Same thing with taxi driving. As we said, even the other cars, even though they are not taxis, they affect the operation of the environment for this particular agent. Some of them may affect him competitively. For example, let's say there is only one parking slot. If another driver enters that parking lot, this particular agent will lose that. Some of the operation may be cooperative. For example, many of the cars that are driving on the road, they will try to make the road safe. So that will benefit them and this particular agent, and so on. But in any case, taxi driving is a multi-agent environment. So that's what we have here. Only Sudoku is single agent, and the rest are multi-agent. So the idea is basically to show you, depending on the agent you are talking about, how do you categorize the environment for that agent in terms of the different dimensions that we have discussed. Or the last subtopic in this lecture is to discuss about the type of agents. We're going to discuss 4 types of agents in terms of their structure in increasing order of generality. So we have model-based reflex agents, goal-based agents, and utility-based agents. Let's start with the simplest one, the simple reflex agents. So for the simple reflex agent, is the one that selects an action only based on the current passage, ignoring the rest of the passage history. Just the current passage is what it will use to determine what to do next. Okay, the vacuum agent that we saw earlier is an example of a simple reflex agent, because its decision is based only on the current location and whether the location contains dirt or not. In fact, this is the program for that particular agent. So as you can see, it will receive its current location and the status of that location, and then it will return an action. So all it does is it will check, is the status dirty? If yes, sock. Else, is the location A? If yes, move to the right. Else, is the location B? If yes, move to the left. And that is it. These are the only thing it does. So clearly, its action only depends on the current passage, and therefore it's a good example of a simple reflex agent. Now, simple reflex behavior doesn't only occur in simple agent like the one we just described. It can occur even in more complex environments. For example, in the automated taxi driver agent, if the car in front brakes, this should trigger some established connection in the agent program to initiate the action, or to take the action, initiate braking. So it can occur even in complicated agents, this kind of reflex behavior. But the idea is for simple reflex agent, that is all it can do. Take an action only based on the current preset without looking at the history. All right. So, but these more complex systems, there are cases where they will have to do a reflex action, and there are cases where they have to do more complicated analysis before they take the action by looking at all the previous history, the internal state, and so on. We will see all of that in a moment. Now, we call this kind of connection where we go directly from the current preset to an action as condition action rule. Okay, so usually agent will have a kind of set of conditions which, if they occur, they should directly take a certain action. Okay, we call this condition action rule. This diagram shows a program in schematic form that shows how condition action rules allow an agent to make the connection directly from the current preset to an action. Okay, and this is actually the way the reflex, simple reflex agents, how they are normally programmed. So this is the agent, and this is the environment. The agent receives a preset through its sensors. It will go through a process called what the world is like now. The preset will tell it the current situation. So all it will have to do, it will go to what action should I do now. But in that action or in that process, it need to consult the condition action rule. Okay, which will direct it as to what to do. So, for example, if it receives preset that it is dirty, the square is dirty, so there will be a condition here that tells it, well, if it is dirty, the next action to do is to sock the square. So it will do that by directing its actuators to actually do the socking. So this is the simplex, or this is the simple reflex action agent, how they are normally programmed. Is there any drawback? Well, there is. The problem with simple reflex agents is that they can only work if decision can be made based on the current preset that they receive. Otherwise, they will be actually in a state of an infinite loop. For example, let us say the simple agent, the vacuum agent, lost its ability to perceive its location. It can only perceive the status of the square, whether it is dirty or clean. So it receives dirty, and the condition here tells it, well, if it is dirty, you should sock. Okay, now it cannot move to the left or right because the percept for knowing its current location is lost. It cannot receive that percept because the sensor for determining the location is lost. So even though there is a condition here that says, well, if you are in A, go to B. If you are in B, go to C. This agent will get stuck where it is because it never receives that it is in A, so it cannot go to B. It will never receive that it is in B, so it cannot go to A. So basically it remains stuck. So this is the drawback in this kind of agents. They can remain in an infinite loop because there is no preset received to direct it on what to do next. Okay, so the next type of agent is the model-based reflex agent. We saw that the simple reflex agent has a problem in that it doesn't keep any history of the presets. It works only based on the current preset. So what this model-based reflex agent does is that it tries to keep some kind of history. So it says here, to handle partial observability, the agent must maintain some sort of internal state that depends on the passed history. So it doesn't just rely on the current passed, and it doesn't keep all the passed history as we mentioned before, but it keeps some kind of internal state which depends on the history. For the break-in problem, for example, it just needs to keep one last frame for it to be able to determine the current situation. Okay, the internal state can be just the previous frame, allowing the agent to detect when two red lights on the edge or the rear edge of the car go on or off simultaneously. So previously, these two lights were off. Okay, it maintained that as an internal state. Now the present passage shows that these two lights are on. So obviously there is a braking going on in the car in front. So that will now direct the agent to know what to do. If it doesn't keep this internal state, which tells it about the history of the previous situation, it will not be able to detect correctly that there is a break-in presently in the car in front. Now, updating internal state information over time requires two kinds of knowledge to be encoded in the agent program. One is the information about how the world evolves, how the world around the agent evolves independently of the agent. For example, an overtaken car will generally be closer behind than it was some moments ago. So if you have a state that tells you how far that car was some moments ago, and now the present passage is showing you how far it is, obviously very close to you, then you know that it is trying to overtake. This is the idea. So one set of information that need to be kept is that about how the world evolves, independent of the agent itself. The second kind of information is about how agents' own actions affect the world. For example, when agent turns the steering wheel clockwise, obviously the car turns right. So the agent has to keep this kind of information in mind. Now, this knowledge about how the world works is what is called a model of the world. So an agent that uses such a model is called model-based agent. Let us see the nature of the program for this kind of agent. So as you can see here, the process here is still the same, what the world is like now. However, this time is depending not only on the current passage received through the sensor. No, it also depends on the current state that the agent maintains. Okay, it also depends on the model. So the model is knowledge about how the world evolves and what my action do. So if you combine all of this, it will now direct it us to know what the world is like now. Of course, once we know what the world is right now, we shall update the current state so that next time we will be using the updated state, not the current one. All right. So these are the information that will help the agent to know how best to proceed, not only based on the current passage, but information about how the world evolves and based on the current state. So with that, now it can proceed to check the condition action rules to decide what action I should do now. So this is the modification to the simple reflex agent. Those ones, they don't keep any previous information at all. But the model base will keep some kind of history related to the previous state that will help to guide it as to what to do. So these are much better than obviously the simple reflex agents. Now, regardless of the kind of representation used, it is hardly possible for the agent to determine the current state of a partially observable environment exactly. And these are just estimates of what the world is right now. To really have a full knowledge, an agent has to keep all the past history. Well, reflex-based agents, they don't do that. But at least this model will allow it to have some estimate of the current situation. Okay, so it cannot see the world fully, but with this, it will have some estimate of the present state of the world, and that will help it to take better decision than if there is nothing at all. Let's move on to another type of agent, which is even more general, the goal-based agent. Now, as well as the current state description, which is normally stored by model-based agents, agent also needs some sort of goal information that describes situations that are desirable. For example, if a taxi agent encounters a junction that has three possible ways, either to go straight forward, go to the left, or go to the right. If it has a goal here could be the destination where it is trying to reach, that tells it that destination is straight ahead, then clearly that will help it to determine which of these three options it should follow. Go straight forward. This is where you're going to achieve your goal, because this is where the destination is going to be. So this is the point. An agent program can combine this with the model to choose action that achieve the goal. And it can combine the information about its goal along with the model that we already discussed for the last type of agent, the model based, and the two combined will help it to decide how to proceed in a better manner. So goal-based action selection can be straightforward sometimes, but more often than not, it actually requires a long sequence of searching. Therefore, searching and planning are the subfields of AI devoted to finding action sequences that achieve the agent's goal. We are dedicating 2 weeks actually learning about searching in this course, another week for learning about planning. So these are very important subfields of AI, and they are all related to finding or achieving a targeted goal. Okay, so we can see how that relates to the agent structure. The goal actually will help the agent in determining what action to take next. Okay, now notice that decision making of this kind involving goals is different from condition action rule, as it involves consideration of the future. In the condition action rule, we already decided if it is this, do this. If it is this, do this. So this can in fact be straightforward. I mean, this can be hard-coded straightforward, maybe even hardware coded, so the agent know exactly what to do based on each condition. But this is talking about the future, so we cannot do it that way. It depends, for example, on what will happen if I do such and such in the future, and will that make me happy? So these are the two points that the agent will consider in determining what action to take next. And obviously this cannot be just hard-coded. It depends on the current state and the goal that the agent is trying to achieve. So let us see the structure of the schematic program for goal-based agents. Almost all of these are the same, like the goal-based, the model-based reflex agents. We still need some knowledge of how the world evolves and what my action do. So all of this will allow the agent to learn what the world is like now, and now it needs to also ask what it will be like if I do action A. So based on this, it will now also consult the goals process. So here you can see we have replaced the condition action rule with goals. It is the goal that will determine, that will help, in addition to, of course, the internal state, the goals will help it to determine what action it should do next before it finally invoke the actuators. All right, so this is the goal-based agent design. The final agent structure is called utility-based agent. This is the most general, actually. So it says here, goals alone are not enough to generate higher quality behavior in most real-life environments. Example, many action sequences will get the taxi to its destination, achieving the goal. But some of these sequences are quicker and safer and more reliable than others. So the question is, which of these sequences should the agent choose? In other words, goals just provide a binary distinction between being happy and being unhappy, achieving the goal or not achieving the goal. But a more general performance measure should actually allow a comparison of different states according to how happy they will make the agent. So instead of binary 0 or 1, we should have some range of values, and the agent will now choose the best one among these values. Often some of these goals are contradictory. For example, being able to reach the destination faster, maybe at the detriment of reaching the destination safer, and so on. So if we have all of this combined in a utility function and then obtain some value, maybe one option that will allow us to reach safer may have better value than another combination that will allow us to reach the destination faster. So this is the idea. In other words, the utility function is not binary. It's like a continuous function, and we are trying to maximize it. Now, instead of using the word happy, economists and later on computer scientists decided to use the word utility, because it looks like utility is more scientific than happy. Okay, so instead of calling the agent happy-based agent, no, utility-based agent. We can note, for example, in two cases, goals are inadequate, but a utility-based agent can still make a rational decision. There are cases where goal-based agents will not know what to do, actually. but utility-based agent can determine what to do even in those situations. These are: 1, when there are conflicting goals, only some of which can be achieved. So the question is, which of these goals should the agent try to meet? So this will be based on which one of them will maximize the utility function. Another case is when there are several goals, but none of which is certain to be achieved. Okay, so again, in this case, the utility function will allow the agent to decide on which of these goals it should pursue. So this is the structure of the utility-based agent. It's very similar to the goal-based. The only difference now is, instead of having goal, we have utility. Okay, most of the other things remain the same. So knowledge of how the world works together with the internal state will allow the agent to know what the world is like now, what it will be like if I do action A, and based on the utility, how happy I will be in such a state. So here it's not a question of will I achieve the goal or not. No, by how much will I achieve the goal? This is basically what the utility function will do. Okay, so based on that, then it will know what action to take, and it will direct its actuators to actually perform that action. Right, so these are basically the different types of agent structures, and later on in the course we shall see how we actually implement them. This is the end of this particular lecture. Thank you very much.